Okay. All right. Hi, everybody. It's Open Source Antibiotics Series 2, meeting on Friday, the 16th of July. And I will share screen to put up the agenda and stuff, which is hopefully this guy. Okay, and we've got a few things to do today. One is to run through some of the ADME data that we had last time and where we've now got some log D data, I think. So we can run through that in just a second, and also going to hopefully get chemistry updates from various people, and asked Alex to come along and just say a few final words, hopefully, about the talks. And Lee is joining us to talk about plans for the mechanism of action experiments. So lots to do. Anyone want to go first? Lee, I guess, did you want to say something about mechanism of action? Because we came back to you with some requests about experiments we could do based on latest data. Just to reiterate what I said on the email, we have been measuring potency versus MRSA and toxicity. And Alex is on the call, has been doing a lot of toxicity measurements. And we've been finding that many of the more potent compounds against bacteria are toxic. And there's a bit of a tracking going on there, not perfect, but some tracking going on there. And so I guess we were very interested in trying to find out mechanism of action stuff. And the idea rose that, what if the target is also mammalian, human? Is there a way that the experiments, if we did them on a MRSA experiment and on a mammalian cell line, that we could maybe extract some information about that to see if indeed there is a human target? I guess that's where we were at. We also haven't yet identified a compound that's better than the ones we sent you, the positive and the negative control. And so I guess we wanted to talk about whether you needed more compound and what the plan was. Are you happy to just to update us and tell us what gives?
Yeah, so, I don't remember what we left off with as the most promising targets. We've been reevaluating a lot of our mass spec runs over the last year. We realized we've been dealing a little bit with the detergent contamination that has sort of suppressed some of our signals. So in some ways, I wouldn't mind repeating what we started off with a new set of MRSA lysates and maybe the top compound. I think in parallel, it'd be great to do these experiments in an HEK 293 cell, some kind of human cell line, so that we can get profiles of both the bacterial components impacted as well as the human cell components. And then it's going to come down to narrowing it down and possibly doing some siRNA experiments to knock out the putative target and see if we see a change in effect. It's a bit of work yet. I think that's where I feel like we need to go though, and I feel like there were what looked like some pretty promising hits from the first set. I don't know what other people have, if anyone else has followed up on some of those things. It's been a while since I connected with you guys.
Yeah, I mean, Giada was on the call, was doing a little bit of modeling on looking at some of these, and we were looking into them a little bit, I guess, but we left it, I think, where you were going to, last we spoke, you were going to repeat some of the experiments just to double check some of these results. But in the meantime, we've had some tox measurements that suggest that we're hitting something that may be a human target too, and we just don't know.
Also, we got reports back about leishmania, that the tox scaled with the potency too.
Mm-hmm, mm-hmm.
So I don't know if I raised this concern a while ago. We don't even know maybe if the target's even protein. It could theoretically, we could have theoretically have a DNA binding agent.
Mm-hmm.
So I don't know how we would rule out if the target's nucleic acid versus protein, but.
Well, it would be a lot easier for us to do these studies in a human cell line because we don't have good access to MRSA samples. I had to go to a lab next door and get those. If there's a great interest in a human target, potential off target, we could certainly do that in 293 cells. And we have a very well-established kinome profile in 293 cells. So that wouldn't take us very long.
Right. I mean, what do people think? I think that we give them the tox, we should probably do that.
What cell line is the tox time?
Well, it's a variety. I mean, I think HEK was one of them, wasn't it?
I'm just thinking, if you're doing this experiment, you should do it in one where you show the toxicity.
Yeah, quite so.
Sure,
Yes.
that's a good suggestion.
I think Alex has been doing them in HEC cells, right, Alex?
I've only been doing stuff in HEC.
Yeah.
I think we've discussed before that other people are doing other cell lines.
Mm-hmm.
You never said you wanted to go that way, so just HEC
Yeah.
for now.
So yeah.
Mm-hmm.
So sorry. So HEK is a good idea.
Yeah.
Okay. I guess,
Would it be possible to look for like DNA damage upregulation, like ATM and stuff like that, to see if what we're dealing with is a transfusion agent versus an actual protein, kinase inhibitor?
we have assays where we blot for DNA damage markers pretty frequently. Yeah, so that wouldn't be hard to do. I don't know, someone else may have the same assays running in their lab.
Yeah, to look just to see if ATM is phosphorylated, because
Right.
this could be DNA damaging agent. We don't know. Because if we pull up the leash toxicity, we also see it scales with human cytotox, which seems like it's either a very conserved target across all kingdoms of life, or this is DNA damaging.
Mm-hmm. Well, just based on what you've told me, I wouldn't be surprised if you see broad ATP competition with some of the either some metabolic enzymes or protein kinases, obviously, that are important for cell viability. But that would be the best direct experiment, I think, to just test a few different concentrations across the profile of where your IC50s are, and look for what proteins are being competed off from the 293 cell lysate.
Okay. I mean, if that is a simple experiment for you to do, then that would be of a lot of interest, I think, because we are, the tox
We have
is-
293s going all the time in our lab, so that wouldn't be hard.
Okay. All right. We just need to know if you've got enough compound, I guess, left over from the last experiment.
I guess Tim Wilson's group has the compounds, right?
They may not have the ones we sent to you. I don't know. We can catch up by email, but based on the last samples we sent, I guess we just wondered if there was enough left over.
Yeah,
Is
I'll
that-
check
that's
with
Okay.
my tech this morning on that.
All right, great, thank you. And I mean, if I'm just thinking about publication as well. So given that we've originated this series as an anti-MRSA compound, it may not end up that way, but if we originated it there, we're going to need to have some data of the kind that's on the screen there in a way that you're happy with. So I mean, if there was a possibility of repeating this at the higher concentration, that would help publication, I think. I know it's more difficult because you don't have the cells locally.
I don't, Dana, do you have MRSA lysates or samples that you know?
Not in our lab. I guess we could get them from Paul, who's the biologist in the building who's been doing the potency testing.
Sure.
But we're just chemistry.
Yeah,
But
it might be a little easier just because I sort of had to ask a lot of favors of the other group to get those samples, and
Okay.
I could go back there if I had to, I guess.
But if we had them, what would how do we work that? What shipping them to you?
Oh, yeah, that's what I was hoping for, domestic shipping rather than international shipping.
Yeah.
I mean, it needs to be dry ice. Obviously, it needs to be a frozen lysate or frozen repellent.
Yeah. Shipping pureed bugs. I mean, that's gonna.
Yeah, that's not a good idea, probably.
Yeah, so Paul's in London too. So yeah.
Yeah, it's gonna be tricky.
Can Well, why don't we do it one step at a time? Let's do the human stuff first, see if we can sort out the toxicity, and then we can think about how we can get a suitable lysate.
Okay.
Okay. All right, great. Thanks, Lee. If that sounds good, then that would be great from my perspective.
Or afterwards, you just call it anti-tumor antibiotic, and everyone's happy.
Generically killing molecule. Great.
Matt, just
Yeah.
can I have some experience with these compounds on this kind of compounds or these scaffolds on Leish and Ticrosai and things like that. And there are some information available that targets for these compounds can be proteasomes on Leish, and I can send you the papers and references in GitHub. And I'm not sure, I'm not completely into this issue, but there are proteasomes that could be a target for for antimicrobials too. And then at some point, maybe this could be something also to study, because for sure they interfere in proteasomes, but and chymotrypsin-like activity of these proteasomes. Okay. So
Okay. Yeah, that'll be interesting.
all these imidazopyridines substitute in the same pattern as we have.
Okay. Yeah, I mean, if you could pop that in on this issue 15 that's on the screen, the mechanism of action, that'd be very useful.
Bacteria have proteasomes.
Yes, I was looking for it, and then I found some reviews on it. Bacterial proteasomes. There are some discussion about it, so could be. I have to read more and to be sure.
Yeah, they have a primitive form, the lawn protease and the CLPP, the clip protease. Those are both proteasome-like in terms of the barrel structure and the ATPase function. So they are like a primitive proteasome. You're absolutely right. And there's lots of interest in compounds. In fact, that's one thing our lab works on, compounds that regulate these bacterial or mammalian homologs of that proteasome.
So that could be interesting to study.
Yeah.
So it's very well possible that this isn't DNA binding, but it's a pan-proteasome inhibitor.
Lee, do you identify compounds with that mechanism of action? I mean, is there a profile that you would see then?
We did, Matt, by accident. We immobilized the compound we were interested in. We captured the mitochondrial protease clip, and that has the bacterial homolog that, and our colleagues have been studying the bacterial ones. There's a lot of interest in both inhibitors and activators of it because they have growth inhibitory effects. And we're looking at cancer cells trying to figure out how that works. But yeah, we used an affinity chromatography approach to fish it out. And that's how we got interested in it. But there's a lot of literature on that area, actually.
Okay, that sounds very interesting. Okay, great. Well, thank you, Lee. That's fantastic. Just let us know if you have the compound enough for the compound to go, and we can supply more if needed. Or yeah, I mean, Tim or Karen might have some locally.
Yeah, I'll check with those guys.
Okay. All right. Awesome. Thank you. Okay. The other thing I wanted to talk about, ideally, so Lee, very welcome to stay on the call if you'd like to. No problem at all. But understand if you have to go places. The other thing I wanted to talk about was the ADME data, because Dana has just added in what was it, the log D data, right? You added in, yeah. So these were the latest data that we got back. And I guess, we're thinking about, well, which compound, what can we learn here? Because last time we looked at these data, we were struck by the, unfortunately, inverse correlation between potency and clearance, with solubility appearing to dominate a number of these features. So we had some compounds like this guy, bizarrely highly soluble with zero potency, and some of our favorite compounds, such as this guy, HU2 down here, with nice potency but dreadful clearance and bad solubility. And so I guess, Daniel included the log D value so that we could have a sort of see whether there's a compound with a nice balance of things. And I guess there are a couple of compounds which are kind of somewhere in the middle there, which you picked out. Daniel, was 865 was one favorite with some potency and things that aren't too bad. But there are some interesting match pairs in here. I mean, I'm really not sure what we do with the data, except try and figure out, what to make next. So with the 5-5 ring system here, that we know is metabolized at this position, if we remove that system and we go for the 5-6 system with essentially identical substituents, so like 865 versus 978 over here, we don't solve the clearance issue, and it's still fairly similar numbers here, which of course raises the idea that maybe there is another liability in this compound. So, for example, the methyl group. But then if you look at the compound next door, which has the O-trifluoromethyl on it, then the numbers are approximately the same. But of course, that could be because it's being metabolized again here. And so I guess, one possibility is a molecule that combines the 5-6 system with something para-substituted, which again is a bit like the OCF3, which would resist metabolic
just make
modification.
an analog of the 865 where we put the 5-6 ring system on, then we use trifluoromethylate, the top methyl.
Yeah, I mean, it's possible. So in this, the 5-6 system with a CF3 or an OCHF2 or something.
Yeah. And
haven't you effectively done that with your sulfone? 837.
Yeah. Beautiful figures here, right? I mean, these are really good.
Yeah.
But just no go on the potency.
So I was actually very interested in 864 because we've made that compound with the para-cyano instead of the meta, and it is active. So I would really like to get ADME data on that, and I've spoken to Lori, and she said she does have the capacity for testing some more of our compounds. So I think that one.
Yeah, that was
priority number one in terms of getting data.
That was an
an
early improvement where we moved the cyano around. Para-cyano was actually pretty good.
Yeah, but the ADME on that related compound is looking like not bad.
But Chris, I guess you're talking about these in terms of, well, this still has the apparent liability here, but we.
That's right. Yeah.
So, which is a little interesting, isn't it? Because you think, well, if these solubility numbers, I don't know your take on this, Chris, but the range of solubility here is just enormous.
Yeah.
With apparently small changes giving rise to very large differences in solubility. I mean, if you look at these two compounds, sorry, no, it wasn't those two compounds, it was these two. So this is a difference of a meta versus a paramethyl. And one is 32 and one is 556. I mean, it's serious differences just with that substitution. I mean, do you believe that? I don't know.
It's difficult to rationalize.
And obviously these are fantastic numbers here, but again, here I guess it's a little bit more sensible, the solubility differences. And clearly there is then not really a big problem with this group if your molecule is soluble enough. Right, so this is one of the examples where solubility is a defense against clearance.
I think that it seems to be that both of solubility and clearance are a little bit driven by log D.
Yeah, I think that's right. Yeah, it's the P450 enzymes are quite a lipophilic environment. So I think what Dan is saying is absolutely correct.
Yep.
So I mean, maybe the inclusion of more ionizable groups as that substituent would help.
Well, not at that substituent.
Well, cyano is quite polar as well.
Yeah.
But for potency, we don't need something polar in that position. We need something polar elsewhere, don't we? Because it appears to be, the potency seems to be tracking quite well with something which is para-substituted. I mean, these groups are really quite nice.
The para functionality, well, cyano on para, and it was polar, and it was water soluble enough, and was very potent. The question arises now, what do we do next? Do we maybe try going from paracyano to maybe paradimethylamino?
Yeah,
Um,
I mean, that's, Giada is actually trying to make the diethylamino, which I also do think would be interesting from an
Sure.
ADME standpoint to look at. But
Yeah.
yeah, those are kind of on the docket.
I mean, something polar or ionizable elsewhere, I haven't really thought of, but clearly that would help if it was in a region of the molecule that could tolerate it.
Would the idea be like how we had on some of the NEU compounds on the pyridine, we had a methoxy, maybe have a cyanopyridine instead of our unsubstituted pyridine?
Yeah, I was actually thinking of on the 5,6 core maybe, because if I remember correctly, then that does also tolerate some substitution. That might
What
be
if
interesting.
we took 978 and then changed out the chlorine for cyanide? Changed it out for a cyano group on 978. Just CN instead of CL.
I guess it depends what's available, right? I mean, what's the simplest thing to explore there? We need a quick scan of starting materials, maybe with things that we can access in that position.
Well, can you functionalize displace the chlorine?
Yeah, and that sounds like your chemistry.
Yeah, I haven't tried, but I was also thinking we would do that.
I was thinking 978, do a Finkelstein reaction, get a bromine, and pop it off with TMSCN.
Yeah,
We don't like Borgfeller-Hartwigs on cores like that, do we?
we'll have to see. I think my issue was that I just had never scaled up that core to get enough to kind of play around with substituting the chlorine. But I had sort of thought about doing that. So
Do we have any 978 remaining?
Not a ton, I wouldn't think.
No.
I don't remember exactly.
It would be interesting to just try reacting that with TMSCN, seeing what happens.
Well,
It
I mean,
should react.
Yeah, I mean, I think, yeah, thinking about maybe what we can put on the core to possibly help solubility or ADME properties might be an interesting way to go.
But if you're going to have to remake it, it might be worth making a compound with a handle that's more useful at that point.
Yeah.
Even if you don't think it's going to be active in its own right.
like bromine.
Mm-hmm.
Wait.
Mm-hmm. I'll have a look at the chemistry for that.
Right. Yeah, log D's 3.1, right? Yeah, it's interesting how well that's tracking actually. Okay. I mean, yeah, one thing to say is a high degree of sensitivity to things in the para position really is quite noticeable. Again, here, and how important solubility appears to be for other numbers. No great surprise, but good to see it. Okay, any other things people want to point out here, just by staring at the sheet of compounds and colors? Anything else striking?
So I just have a quick question. Has Laurie forwarded any of the ADME data that we have for the N-alkyl compounds to you also?
Yeah, so this was just the latest batch of things.
Sure.
So sorry, let me just bring up the master page. Where am
I'm
I?
sorry, I don't know that I've done a great job about updating this, but maybe it's there. I'm sure she's sent it, Quillon. So I think we have it. I don't know if I've gotten around to doing a sort of more in-depth analysis of it.
I actually forget where I'm looking for this. I thought we had a page on this, but I'm suddenly not seeing it. Why am I not seeing it?
Maybe my fault. Because it should be under the metabolic clearance stuff, but
Sorry, Dana, I didn't mean to throw you under the bus here.
No, you're good. I mean, some of these are from NEU, I think. And this would definitely be data, obviously, NEU that Laurie had sent to me. And there, I can't remember exactly. There possibly is more, but yeah.
Yeah, because, okay, I can see a few here. In general, I could have a look through this, and if you could let me know what has been sent, Dana. And I could send compounds that perhaps you haven't seen or tested, but I can still provide ADME data for, like, more generally speaking, so you can see the SPR for the series as a whole. If you're interested in that, I can send through some of that data if it hasn't been done so already.
That would be great. I guess I'm just looking at this now, actually, and looking at some of the solubility figures and some of the clearance data. It's not completely tracking, right? Because for 856, without anything and with no aromatic ring as R2. Okay, no, that must be R2 is H on the ring, right? R2 here is an aromatic ring, and that means it's not substituted, right? No, it doesn't, right? It means there's just H.
Yeah.
Oh, right, okay. Because this is highly soluble, but it's cleared fast.
Yeah, and yeah, not active, which is not surprising. So it's basically just what happens when we remove that substituent entirely.
Right. Right.
I think the carbon-carbon linked ones are also could be quite flat. I would expect that they maybe would be. So that could be part of the problem as well.
If we dumped all this data in Data Warrior, we could get a 3D plot, right, of MIC, log D, and microsomal clearance.
Yeah. Is all the data in the master sheet?
Yeah, so the master sheet should be completely up to date, as I try to do that first priority, and then the wiki.
Yeah, so yes, and there is a macro that enables you to do that then.
Yeah, it sounds familiar, Chris, actually.
I thought I'd get that plug in.
So maybe we should do that plot then and see if there's an outlier. That would be useful. Okay.
Yeah, so something that we found is that if you do the N-alkyl derivatives, they tend to be more soluble than the free NH. So it could be a geometry confinement issue as opposed to a purely log D driven solubility correlation.
Well, that chain one would assume wouldn't make it that flat. It would be a little more character. There was a compound I had talked about a while ago, putting like an ethyl oxetane in that position to try to break the flatness.
Okay. All right. All right. Thanks. So we are a couple of targets there and a couple of ways forward. I'll put actions up on the minutes, but trying to access perhaps other compounds here from our precursor to try to improve the solubility again. So often the case, you're trying to improve the solubility of things. Okay, so does anybody? Oh, so Alex, so you've been sitting on the call, and I just wondered if you wanted to say anything about talks. Shall I unshare if you want to say anything?
I mean, I still have my table, and I can share that and talk through it again. But I mean, it's not. It changed much since last time. So
yeah, I mean, if just to remind us.
Okay, yeah, I can do that. Does everyone see that? Yeah.
Yep.
So for those people who have not been there when I presented before, also because I don't make it every time. So we've been looking at toxicity of these compounds that I was given in HEC 293, and initially I started with the quad protocol, well, trying to reproduce that, and their readout is resazurin, so fluorescence readout. However, our preferred method is MTT, which is a tetrazolium dye, so absorbance-based measurement. So I compared those two following the same protocol, which essentially is incubating, well, seeding the cells, incubating for 48 hours to reach some sort of confluency, and then treating for 24 hours and reading afterwards. And from that, I sort of got IC50s or CC50s ranging from 1 to 10, which in micromolar is about 3 to 30, I guess, for 10, for an average molecular weight of 300. I think the issue that I had with these was that the standard error is quite high, sometimes 20 to 25%. So I wasn't sure why that is. Also, there's a big discrepancy for 983 between the resazurin and the MTT readout, where I couldn't calculate an IC50. And for MTT, we can, and actually the inhibition is quite a lot higher than what we find by resazurin. So then the other thing we wanted to do, because this is actually typically the way we do a toxicity assay in our lab, is seed a sort of smaller number of cells, allow them to reach exponential phase. So typically here I incubated for 3 days before treating, then we treated for 24 hours, and then we allow the cells to recover so as to see if then they actually, if the compound is actually just cytostatic, just holds proliferation, or it actually cytotoxic, and if the cells then don't recover, then that's the case. So I haven't done a great deal of these because they're longer than this one, and haven't had much time, sorry. But what I can say, and I wanted to clarify this issue for 983, so I did both readouts, and as you can see, I get fairly similar values for the CC50, and the standard error is much lower. So for me, I'm a lot more confident in this data, also because it, from our point of view, it makes more sense to do it this way. So in terms of the order, neither by resazurin or MTT, that doesn't change, and sort of, yeah, they still seem to be quite toxic, at least the ones that I've tested. So.
But the resazurin in 1 week, what are the numbers telling us there?
So again, it's just a difference between the actual protocol. So rather than seeding the cells, here I seeded 5,000 cells in 48 hours. Because I'm doing the assay in a 96 well plate. The Klug protocol used a 384 well plate, so they seeded 5,000 only for 24 hours. But because I'm using a larger surface area, I allowed them to grow a bit longer, and then just incubated with the compound and assayed after 24 hours. For 1 week, so what means 1 week is because I incubate for 3 days, allowed to go to exponential phase, treat for 24 hours, and then allow for recovery, or washout, as Dana called it, for another 3 days, and then assay. That's why it's 7 days in total. And the readout is just MTT or resazurin. I just wanted to see if by using this method or protocol, whether I would see again the discrepancy from 983 in the readout, and it's not the case. Although the lowest sort of the maximum inhibition is a little bit different, but the overall CC50 is not. So,
What does it say? Sorry, Karen.
Oh, sorry, just had a question about the 1 week assay. So would that also tell you whether your compound is cytotoxic versus?
Yeah, so that's the point here, right?
Okay.
You insult the cells in some way, so of course they're bound to, oh, hang on a minute, what's going on? I'll just stop proliferating for a while. But then if you remove said insult and you allow them to grow further, and compared to the control, you will see whether that's actually cytotoxic or just static. So
static. Okay. Yeah. Cool. So it looks like these are toxic.
Yeah.
Okay.
Not
good
static.
Good to know. Yeah. Okay.
They also look to be much more toxic in the 1 week assay than they are in the 48-hour assay?
So yeah, I haven't done every one of them, but by MTC, that's not really that different. But as I said before, here the standard error is quite high, so 20 to 25%, whereas this is like 1 or maybe less than something like that. Yeah. So by this readout, and that could be due to various practical things to do with the two assays. As I said, rosazurin is a fluorescence readout. It's you have a higher dynamic range. You have the opportunity to not have to wash in between. So you add the dye and just read in the well, whereas with the MTT, it's often you have to remove the solution, wash, you have to add the MTT solution and then remove again, and then add the MSO to solubilize the crystals. So there's a lot more error that could come from these many steps. So, or you could lose cells because you're aspirating many times. Yeah, so those are the practical differences.
Right. So this is great for publication. Are you happy to complete some more of this, in the sense that I'm thinking on the right there with the residue?
Yeah.
I mean, not necessarily everything.
I think it's no, I can do that. I can't say how long it's going to take, but I guess we're not publishing it in the next month or so, right? So. Well,
I mean, it depends on some of the last potencies here and some of the mechanism of action. But yes, I mean, getting results back from the mechanism of action stuff is going to take a few weeks based on what Lee just said. Okay. I would guess. I don't know. We'll wait to see what he says. So yeah, I'm just trying to make sure that we do have a set where a referee from for a paper that you typically publish, Alex, isn't going to say, hang on a minute, whereas all the rest of it.
Yeah, so I mean, again, right, there's many other compounds in those series that you showed. I don't know, do you need to include sort of this data for all of them? Or, I mean, I have more data for some and less data for others so far. So, yeah.
No, I don't think we need tox on everything. I mean, this is a representative set. If we come up with a much more potent and effective compound, then we may need to measure that. But at the moment, I think this is a representative set.
Okay.
So yeah, it's just more about, crossing the T's, dotting the I's.
Yep.
All right, fantastic. Thank you. That's really good.
Should I stop sharing now?
Yeah, okay. And then, so yeah, I wanted to also mention the compounds that were sent through from NEU, which is great. So we are the lucky recipients of these compounds, which have just arrived, and which can be included in the next round of potency evaluation. So thank you very much, Laurie and Quillon, for sending those over.
No problem. You're not sharing, just as an FYI.
Always got to hit the share button. So these guys, right?
Yeah, that's right. So those are the compounds that we've just sent through. I'm sorry that we didn't have enough of 2 that I mentioned in the previous week. They were sort of a bit shy for our own projects. So these ones I had access of, so I was able to send through.
Fantastic. That's great. Thank you so much. That's really good. Did you want to, so I just want to invite anyone who wants to give a chemistry update to briefly update everybody. If anyone would like to say anything about, current efforts.
Yeah, just a brief update from my side. I believe now we have some examples from the homology series, but we are not very successful in having very good yields, problems on purification. So we have them, but in just a small amount. Maybe I will contact Laurie and the guys and their team to help me on how to purify. I think last meeting I participated, someone mentioned that there was also an issue on bisalkylation of the amines or something like that. And this was something that
you did that isobutyl compound, right? You got a bad yield on that, right?
Yeah.
Sorry, could you just fill me in? Could you say which compound you're trying to alkylate at the moment?
Wait a minute.
sorry.
So the series that Flavio is talking about is this,
Yeah.
Okay.
with this CH2 between the rings. That's the homologous side arm. And I guess, Flavio, you're talking about putting groups on the nitrogen?
Yeah. There is one, it's phenyl groups, like benzene, like the ones we are working on. And I
Right.
have to alkylate that to keep working with the same kind of substitution. And alkylation is not working that well for us. I will try to I try another method now, just copper alkylation, a radical alkylation now, which maybe could work better, but it will be a different kind of chemistry from the simpler substitution.
Sure. So for the homology units, I actually made a couple of those here at NEU. I installed that via reductive amination. Do you want R and R prime to be separate, as you sort of have it up here? So you want those to be different.
Yeah.
Could you try reductive aminations to access that?
Yeah. I will.
Because that's how I installed them.
Okay.
When you have the nitrogen without the methylene linker there, the reductive amination fails. But when you have that the further linker, the reductive aminations have been fine. So I was doing that with the aldehyde on the actual core itself.
Okay. So I will try, test, and then if it works or not, I will contact you back and have any tips from you to support the guys.
Sure.
Cool.
Great.
That's great. And Quillon, your guys are still looking at alkylating these guys, or some of these guys, right? This transformation?
Yeah, that's right. So I can actually say that I prepared some slides. I can't actually share them though.
Yeah,
sorry.
Great. All right.
Bear with me one second. So we had an undergraduate working on these, and I took over this week to sort of finalize because he's no longer with us. So these alkylations have all gone forward. Conditions up the top here for that. I tend to find that the best way to purify these compounds is using a biotage C18 column. So on about 100 milligram scale, I'm using their 30 gram C18 column to do the reverse phase purification. If you have the isobutyl, it tends to give you enough separation between the bis-tris alkylated species and the remaining starting material. If you have smaller alkyl chains, we are not able to do that. We send it away to get professionally purified. So I've been able to isolate these four that we have down the bottom here. The exception is this final compound here. There's only a few milligrams, it looks like. I'm waiting to remove the last of the water from the column. If it came to the choice between obtaining host cell tox data or ADME, do you have a preference of which data you'd like us to share through? Because it may have to be a choice with this one here.
I mean, ADME is always really useful, particularly in this case, if we can include in the measurement log D that, and if that is part of your ADME screen normally.
Yeah, we get a full tier 1.
Okay, so then this would be particularly useful because it has the ortho substituent, which should help with solubility, right? Because it deplanarizes.
Definitely does. So I can, just as a little bit of extra information, as part of our efforts, I've been growing crystal quality structures for these. So these are some X-ray crystal structures that we've got for these compound series, and a bit of the ADME to go alongside that.
Oh, beautiful.
And yeah, definitely improves the solubility with that orthomethoxy compound. As you can sort of see here, it's non-linear. I think it precipitated out at the top end of the curve. But yeah, unfortunately for us, it completely kills potency when you twist that ring. So if you were able to get potency with that, then there's definitely avenues to improve solubility through functionalization of that pyridyl.
Wow, nice.
So that's interesting.
Mm.
So if you twist, you lost activity. So
Yeah,
maybe-
almost complete loss of activity for us.
yeah, maybe if it keeps that idea of that forming site for complexes, it's important. Having these piperidine-like compounds.
Yeah, it almost sort of alludes to a hinge binder, but it's not quite the proper motif for that.
Yeah, we were thinking.
It's really interesting the impact it has on solubility, though, isn't it?
Yeah.
Yeah. So I think for us, the issue is that the NH compounds stack a lot. The crystal volume between these two compounds is very dramatic. So that small twist actually stops it stacking in the actual crystal lattice. And then from that obviously then affects the solubility.
Yeah. I mean, I think something like this might be going on with some of the compounds we were looking at earlier with like the the meta versus the para substituted.
Yeah, so I did a very rudimentary sort of modeling of that, and it does appear that if you have the ortho substituent, that methyl group can get underneath and sit when you have the direct CH linkage. So obviously that would affect the stacking ability of those compounds.
Yeah, I mean, you can see the solubility difference is quite dramatic when you can change the conformation.
Yeah, it is quite an interesting one, this actually, because normally you associate big groups which clash with giving these large angles. Here you have heteroatoms, which don't necessarily have H's sticking out. So the oxygen doesn't have an H sticking out, and the nitrogen can be either way around and not have something pointing at the other ring. So it's nice to see that it is still a dramatic impact, in fact.
Yeah. So we've also done some energy minimizations of these two compounds as well. And at a B3 lip level, you actually see the pyridyl rotates completely around and forms an NH bond with the amine.
Okay.
So it's obviously like X-ray, the caveat here is that it's in the solid state and the solution state may behave very differently. But then you got to then sort of weigh that with the QM models that we have as well and how believable they are.
Do you include a solvent in those, or is it gas phase?
Yes, so we've done gas and water phase.
Okay.
Yeah, there was minimal change. The relative change was negligible.
I would have thought water would change that totally. That's interesting.
Yeah.
Just because that would make it less soluble, right? If you're occupying an internal hydrogen bond, it's less available for interaction with the solvent.
Yeah, exactly. But it didn't seem to.
Fascinating. All right, great. So yeah, okay, there's a reason for getting the ADME on that compound rather than the tox.
Sure, no problem. So three of the four I can send to you for activity. I'll see if I'm able to purify that remaining fluoro compound. Sorry, the 6 fluoro in the core.
Okay. All right. That's fantastic, Quillon. Thank you. Well, a very quick picture I just got from Giada, who's still with us, who I think has this red compound nearly pure. Giada, do you want to fill us in?
Yeah, so basically last week we synthesized the red compound, but we didn't obtain like 100% pure, but we have only 90% pure, and the yield was not really good. So we tried also to obtain the same compound by different intermediates, by different steps, but as well we didn't obtain the desired product. So the plan is try to purify again the compound, the red compound, and test it, and next week try to optimize the synthetic route in order to obtain more compound or more pure compound.
Great. So the profile hardware is working on this core, which is, I mean, to some extent, which is good.
Yeah.
Yeah. All right. Fantastic. Thank you. Yeah. I mean, of course, that's enough compound for us, right? For this. So if you can get something similar of that is pure, and then another compound on the same kind of scale, that's enough for doing the biology. See how you go.
Yes, the one.
Yeah, fantastic. Okay. All right. Anyone else want to say anything about chemistry?
So yeah, I'm still on the 1 pots. It looks like 5 minutes in the microwave as opposed to 30 is actually helping.
Really?
So, and then it's just the purification. They're horrible to work with, really. The crude is like black and it's gross. But I have done the Purol, a normal phase column. The NMR and the LCMS look okay, but the material's still black, so I think it does need another purification. But I'm hopeful about that.
I'm guessing a lot of that formal pyridine probably polymerized.
Yeah, it's
So it's a risk.
not pleasant, but I think I will get compound out of it. So I'm optimistic.
Did you say that you do normal phase purification for this, Dana?
As a first pass, yes, but normally it requires reverse phase after that.
I can send you through do you use a biotage system?
Yeah.
I'll send you the graph for the conditions that we use.
Okay.
It's a generic method. It's sort of almost a catch and release method. So it will precipitate out at the top of the column. You wash out all the impurities, and when it gets to a certain percentage, it redissolves and puts out a pure compound. It makes the purification of the 1 pots trivial.
Yeah, well, so the thiazole one, I actually went to purify that reverse phase and ended up recovering it just from washing it basically with methanol. But that's not working for the Purol derivatives. So the solubility of those does seem to be a little bit different. But yeah, if you want to send me that, I can give it a try for sure.
Yeah, I've used the same method for about 80 of these compounds now.
All right.
So it's super general.
Fingers crossed. Cool.
Yeah.
Okay, thanks, Quillon.
Of course.
And if it doesn't work, it's the biotage's fault, Dana. All right.
Yeah, not mine.
Or blame the column. They get old.
Okay, great. I think we're running out of time, unfortunately, but I think we've covered pretty much everything. Quillon, are you on GitHub already? Did I miss that?
I've just made an account yesterday.
All right, great. So I can tag you here, and we can stay in touch there. That's fantastic. Okay. Any other urgent things that people want to mention? All right. If not, then great. Thank you very much for your time. And I'll put up some notes and actions after the meeting. But great to see everybody. See you again soon.
See you there. Bye.
Bye.
Bye-bye.